Hello, and welcome back. We're going to cover a couple things that are this kind of adders onto momentum. Have to do with the center of mass, which we've covered, and conservation of momentum in two dimensions, two directions. So, a little bit about center of mass. You probably have an idea what the center of mass of an object would be. If I were to throw a ball or a piece of wood in the air like these, it would spin about the center, okay? And that's where their center of mass is. It would be in the center of the object. If it's uniform, meaning it's made of the same stuff throughout, and there's lines of symmetry, it's just where those lines of symmetry cross, aka the center of that object. If we look at a little bit more of a complex object like a hammer, okay, the hammer doesn't go about its middle, which would be right about here. It goes about a point that's much closer to the heavier hammerhead. So the center of mass of the hammer is closer to the heavy head because it's got more material down there. If you were to put your finger under that, that's also where it would balance. So that's the center of mass of an object. It's kind of the average location of the mass. So if you've got more mass towards one end, the center of mass shifts towards that end. So here we've got a similar object. We've got a wrench, and a wrench has a lot of metal in the jaws of it. And what they've done is they've given this wrench a spin and a push, and you can see that that center of mass of the wrench follows a nice straight line, and so it's rotating about its center of mass, and that center of mass is just following a straight line. Okay, so that's how objects behave when about their center of mass. If you were to throw a baseball in the air, the baseball would follow a parabolic path. If you were to throw a baseball bat in the air, which I don't recommend, it would look a little bit more random, the motions of the bat. But really, what it's doing is two things at the same time. It's rotating about its center of mass, okay, which is towards the fatter end of the ball. Okay, so we've got this thin handle, and we've got this fat end, so the center of mass is shifted towards that fatter end. And so it's rotating about its center of mass, and that center of mass follows a parabolic path just like the baseball did. Okay, so if there are only internal forces involved, okay, like basically the conservation momentum problems that we're going to work, a collision or explosion does not affect the center of mass of the system. Does not affect the center of mass of the system. So here we've got a firecracker, and I'm going to explode it. Initially, my center of mass is stationary, okay, and afterwards, okay, where's that center of mass going to be? Okay. Well, it's still going to be right in the middle here. It's going to be in the middle of those two masses, so it's going to stay put. It's going to stay right where it is. Okay, so that explosion, which was an internal force, does not affect the motion of my center of mass. Okay. If the fragments are in different sizes, okay, the center of mass is going to be closer to the fatter one, and so it's going to end up remaining right where it is, right here. Okay, so the center of mass in this case is just still going to stay right where it is. Okay, and I've seen a question along this line on the AP exam. But basically, if this baseball bat were to explode into different pieces while it was in midair, okay, that internal force would not affect the motion of the center of mass, and that the center of mass of those exploded pieces would still follow this parabolic path. How would this work with a collision? So let me turn on my center of mass. So this X marks the center of mass, and so this red ball is going to move, and you're going to see that the center of mass is going to be moving to the right. Okay, because the red ball, the mass is moving to the right. Notice what happens to the motion of the center of mass during and after the collision. Okay. It wasn't affected. Okay. It was moving to the right at some speed, and then afterwards it was moving to the right at some speed. So internal forces don't affect the motion of the center of mass. Is kind of the rule of thumb there. It's kind of the deal there. Okay. So real quick on that, and also fairly quick on conservation of momentum in 2 dimensions. So let's say we have 2 cars and it's on ice and they can't stop. They hit. What direction is the wreckage going to slide? Okay. It's going to slide off at an angle. Okay. So initially the red car started with x momentum. Okay, and the y car started with y momentum. The blue car started with y momentum. Afterwards, the wreckage is going to have both x and y momentum. I have rows here that should be p's. Okay, so basically, however much x momentum I start with, and this is conservation momentum in 2 dimensions. Your x momentum is conserved and your y momentum is conserved. You just have to look at them separately. So it's no big deal. It's just another equation you have to write. So however much initial x momentum you start with is how much x momentum you end up with, and however much y momentum you start with is how much y momentum you end up with. So it's not really anything new really. Let's just work a problem as an example, and then that'll pretty much be the end of today's notes. Okay, so here we've got a yellow ball moving to the right in the x direction at 1.1 meters per second. And here we've got a red ball that's moving upwards at an angle of 60 degrees at 2.3 meters per second. They're going to crash and stick together. And what is the direction and velocity that they move off together with? So the first thing we need to do is take this diagonal vector here of 2.3 meters per second, and we need to break that up into its component vectors. So that gives us, I do that right here. So sine of 60 times 2.3 gives us 1.99, and the cosine of 60 times 2.3 gives us 1.55. Okay, then we're going to start off in the x. It doesn't matter if we do the x or the y first. I'm just going to start off with x. So we look at the yellow ball first, okay, and it's got positive 1.11 times 2, okay, mass times velocity, plus the mass times velocity of the red ball in the x direction. So the mass is 3. The velocity is 1.15. That's what we got as the x velocity here. So that's going to equal the final x velocity of the thing that's stuck together, which is 2 plus 3. And we get the Vx equals 1.13 meters per second. So that is our x velocity. Okay. The next thing we look at is in the y direction. Okay. And for our yellow ball, it's only traveling in the x initially. So it does not have any x velocity. I'm sorry, any y velocity. The red ball does have y velocity, and that is the 1.99 that we found here, okay, times the mass, which is 3, okay, and that's going to equal the final y momentum, which is 5 times the vy. So I found my vx and my vy. Okay. Now just to figure out which way the thing is going as a whole, we make a new triangle. So this is my x velocity, this is my y velocity. And the resultant r squared equals 1.13 squared plus 1.19 squared. Okay, using Pythagorean's theorem gives us 1.64. And then using the tangent function, 1.19 divided by 1.13 gives us 46 degrees. And that's it. So it's just basically like two little problems instead of one if you've got it in 2 dimensions. I mean, they might ask you, was momentum conserved in the x direction and y direction? Maybe you only have to verify that it was, or something along those lines. But I don't think that'll be too challenging for you guys. Okay, and that is that.